Welcome to Statistical Inference. Today, we are going to explore one of the most fundamental concepts in decision making, type 1 and type 2 errors. Whenever we test a scientific claim, we are forced to make a decision based on limited data. Because our data is never perfect, we always run the risk of making a mistake. Understanding these specific mistakes is essential for any statistician, scientist, or engineer. Let us dive in. To understand how we test claims in statistics, let us start with a familiar situation, a criminal trial. In a courtroom, the fundamental rule is that a person is innocent until proven guilty. The judge must make a final decision based entirely on the evidence presented. In statistics, we have the exact same setup. We start with a default assumption, which is like assuming innocence. We call this the null hypothesis. It usually means there is no effect or nothing new happening. The alternative hypothesis is the new claim or theory we are actually trying to prove, which is like the prosecutor trying to prove guilt. Now that we understand our starting assumptions, let us look at the mistakes we can make. Since we are making decisions based on limited evidence, there are two terrible mistakes possible. First, we could reject the null hypothesis even though it is actually true. This is a type 1 error, and it is exactly like convicting an innocent person. Second, we could fail to reject the null hypothesis when it is actually false. This is a type 2 error, which is like letting a guilty person walk free because there was not quite enough evidence. You cannot completely eliminate both mistakes. If you make it extremely hard to convict anyone, you will automatically let more guilty people go free. Before we move on to the math, let us see this dilemma visually. What you're looking at is a decision matrix that maps out all four possible outcomes of a statistical test. The columns represent the hidden truth of reality. Either the null hypothesis is true or it is false. The rows represent the decision we make. Either we reject the null hypothesis or we fail to reject it. If reality and our decision match, we see the green boxes representing correct decisions. But if they cross, we hit the red boxes. A false alarm gives us a type 1 error and a missed detection gives us a type 2 error. Now that we have seen the matrix, let us define these errors mathematically. We use the Greek letter alpha to represent the probability of making a type 1 error. This formula tells us how to calculate it. Alpha equals the probability that our observed data, represented by X, falls into the critical region, represented by C, given that the null hypothesis, H0, is actually true. The critical region is simply the range of extreme values that would cause us to reject the default assumption. If we make this critical region smaller, the value of alpha decreases. This means we are less likely to raise a false alarm, but it will affect our other error rate. This inverse relationship leads us directly to our second formula. We use the Greek letter beta to represent the probability of making a type 2 error. Beta equals the probability that our data, X, does not fall into the critical region, given that the alternative hypothesis, H1, is actually true. In plain English, beta is the chance that our data looks completely normal even when something special is actually happening. Because our evidence was not strong enough to cross the threshold into the critical region, we miss the real effect. If you change your rules to decrease alpha, you automatically increase beta, making it much more likely to miss a real discovery. While we want to minimize our mistakes, we also care deeply about our successes. This brings us to the concept of statistical power. The Greek letter gamma represents the power of the test. The formula is beautifully simple. Gamma equals 1 minus beta. Power is the exact mathematical opposite of a type 2 error. It is the probability of correctly detecting a real effect when it actually exists. If you want to increase the power of your test, you can increase your sample size to get more reliable information. You will also have higher power if the true effect size is very large, or if you're willing to accept a higher alpha, meaning more false alarms. Before we calculate probabilities, let us see this with a concrete physical example. Imagine a factory producing metal rods that are supposed to be exactly 10 centimeters long. Our null hypothesis is that the machine is working perfectly, so the average length is 10. The alternative hypothesis is that the machine is broken, so the average length is not 10. The manager sets a rule. They will stop the machine if a sample of rods has an average length less than 9.5 centimeters or greater than 10.5 centimeters. This specific range of extreme values is our critical region. We are setting up the boundaries for our decision. Now that we have our factory rules set up, let us interpret the errors. A type 1 error happens if the machine is actually working perfectly, but by pure bad luck, our sample average is 10.6. It falls into the critical region, so the manager stops a perfectly good machine, wasting valuable time and money. On the other hand, a type 2 error happens if the machine is actually broken, perhaps producing rods of 11 centimeters. But our sample average happens to be 10.2. Because 10.2 is not in the critical region, the manager fails to stop the machine. The physical consequence is that the factory ships defective rods to angry customers. Now let us move to a fully calculated example using a coin flip. We want to test if a coin is perfectly fair. Our null hypothesis is that the probability of getting heads is 0.5. Our alternative hypothesis is that the coin is heavily biased, and the true probability of heads is actually 0.8. We decide to flip the coin exactly 3 times. Our strict rule is that we will reject the null hypothesis only if we get exactly 3 heads. First, we need to set up the calculation for the type 1 error, alpha. We are looking for the probability of getting exactly 3 heads given that the coin is actually fair. Continuing with our coin flip, let us calculate that type 1 error. Since each coin flip is an independent event, we simply multiply the probabilities together. For a fair coin, the chance of heads is 0.5. So we calculate 0.5 to the third power. This gives us an alpha of 0.125 or 12.5%. This means there is a 12.5% chance we will falsely accuse a perfectly fair coin of being biased just because we got lucky and flipped 3 heads in a row. Now we must set up the calculation for the type 2 error, beta, which is the probability of failing to reject the null hypothesis. To find our type 2 error, we need the probability of getting fewer than 3 heads, given that the coin is actually biased with a probability of 0.8. Instead of calculating the probabilities for 0, 1 and 2 heads separately, we can use a mathematical shortcut. The probability of getting fewer than 3 heads is exactly 1 minus the probability of getting all 3 heads. We substitute the biased probability of 0.8 into our equation, so we need to calculate 1 minus 0.8 cubed. 0.8 to the third power gives us 0.512. This simple subtraction will give us our final probability much faster. Finally, we complete our subtraction. 1 minus 0.512 gives us a beta of 0.488 or 48.8%. Let us interpret what this final answer means physically. If the coin is heavily biased towards heads, our 3-flip test is so weak that we have nearly a 50% chance of completely failing to notice the bias. This is a terrible error rate. To fix this and increase the power of our test, the best approach would be to increase the sample size by flipping the coin many more times. Having calculated these errors, we must understand why balancing them is absolutely critical in the real world. In medicine, a type 1 error means telling a perfectly healthy patient that they have a deadly disease. This false alarm causes immense stress and leads to unnecessary, painful treatments. However, a type 2 error means telling a sick patient they are perfectly healthy, which could delay life-saving treatment until it is too late. Engineers face this daily with spam filters. If the filter is too aggressive, you miss important emails from your boss. If it is too weak, your inbox is flooded with junk. The entire goal of statistical design is to balance these two risks based on which mistake is more dangerous. We have covered a lot of ground today, so let us review the key takeaways. Remember that the null hypothesis is always your default assumption, while the alternative is the new claim you are testing. A type 1 error measured by alpha is a false alarm, where you reject a true default. A type 2 error measured by beta is a missed detection. They have a strict inverse relationship. Finally, the power of a test, which is 1 minus beta, tells you how good your test is at finding the truth when a real effect actually exists. You now have a solid foundation in statistical errors.